So this is part of my PhD project, being co-supervised by Jennifer Galloway and Tim Patterson at Carleton University, and of course, Geological Survey, and funded by ArcticNet. Um, so the Mackenzie River Basin is located in the Western Canadian Arctic, and I'm studying this region specifically because of the phenomenon called Arctic amplification, where Arctic regions are warming around twice as fast as the global average. So the northern river basins are particularly sensitive to climatic change. And this is partially because of the distribution of peatlands. So this is just a figure showing the global peatland distribution. And in case someone doesn't know, peatlands are just permanently waterlogged wetlands. As you can see in this figure, they're predominantly found in the boreal and subarctic regions. They occupy around 3% of the land surface, but they are a huge carbon storage, more than the entire forest biomass. Unfortunately, around 10% of peatlands are affected by human use. So that is partly why I'm studying them. This is the distribution of peatlands in Canada on the left, and on the right is just the river basins in Canada. So the blue area, oh, I guess I should use the, where is the, well, okay, so I guess the blue region on the right figure is the largest river basin in Canada, but I'm studying this little outlined region here. So if I were to just superimpose that, it actually occupies a big area of the peatland distribution within the Western Canadian regions. So this is the Mackenzie River Basin. It's one of the largest drainage basins in the world, and it's the primary source of Canada's freshwater output into the Arctic Ocean. Communities living around this region have reported decreased water levels, flows, drier conditions, thinning ice, and generally warmer temperatures. My study area is in this red box here, and there's a few peat cores that were collected mainly in the confines of the Mackenzie River Basin itself, and a couple on the outside. Important also to note is that this is where the Gwich'in settlement area is located, which spans the Yukon Northwest Territories and occupies around 16,000 kilometers square of land, and around 5,000 people live here, with the majority in Inuvik. So just to go back here for a sec, the purple ones are the MAC cores, which are the core P cores that make up the majority of this project. And then there's some other cores that were collected opportunistically, which I call the 16PS and 18GT cores. So the 16PS cores were collected opportunistically by GC officers Fish and Duchenne. I think this was collected during actually a geologic bedrock mapping expedition. Similarly, the 18GT cores were also collected opportunistically, and this was in the Smoking Hills area outside of the Mackenzie River Basin. And this is just my supervisor here collecting a peat core using a shovel. And then the MAC cores were collected in 2020 during the pandemic by Sarah Lord at the Gwich'in Renewable Resources Board. They also collected surface moss samples at other sites, but the peat cores that go at depth are MAC S1 to 4. So these are just some photos of the team collecting and measuring and storing them. The MAC cores were collected by a Wardener titanium core that was designed and built by researchers at the University of Alberta. These ones were frozen immediately upon collection, whereas the other cores were sort of just in the fridge for storage. So these are the highest integrity cores that we have. Some field measurements that were taken were depth to water table, pH, and electrical conductivity. The most important of which for this project is the pH. So On the left here is the figure for the pH measurements of all the peak cores for the MAC sites. And then this one that has been highlighted is MAC S3. So this is the only core that has a pH of less than 4. So this is the only ambrotrophic bog, which means this is the only peak core whose water source is solely from precipitation. And this means that it preserves the well preserves the atmospheric metals and fossils. This is part of the subsampling plan. So this is just some of the peak cores that we see, and then they were sliced down depth, and then each of these slices were subsampled and sent for various analyses. And then there are a lot of analyses and collaborations. So this is a list of just all of the people involved in this project and all the analyses that have been done. So I'm mainly focused on the paleontology, but I did want to give credit to all of our collaborators, especially those at Geological Survey, both in Alberta, out in the east, and Quebec, and in the Atlantic. So there's a lot of things going on at once. But for this presentation, I'm just going to discuss the part that I'm looking at specifically. So the plant macrofossils were important because I needed to sift through them, each of the slices, and pick out the suitable plant macrofossils that can avoid the hard water effect when I submit it for radiocarbon dating. So they had to be specifically non-aquatic mosses, so that they weren't just floating in the water and then giving anomalous ages. So as we all know, plant macrofossils can establish peak chronologies and also give us insight into past vegetation change. Sometimes it was hard to pick the right mosses because sometimes it was the only moss available, but it was an aquatic moss, but what can you do? But the most important ones are, of course, sphagnum, which is depicted on 13 to 18 here. And I had help by Mariusz Galka at the University of Łódź in Poland to help me identify these. So here are some of the peak chronologies, pretty decent for peak cores. This is the 16 PS cores, around 2,600 calibrate years for present, and then 1,300 calibrate years present for the second one. This is for the GTE cores, which were significantly smaller than the other cores. So the one of the cores is actually all modern samples at 60 calibrate years per present. And then we have the MAC cores themselves, the oldest of which is MAC S2 on the top right here. And then MAC S3, which I'm mainly focused on today because it's the best core and is the one that preserves the metals the best. And then we also have some funky looking ones like the MAC S4, which is on the bottom right, which have a lot of age reversals. These are just some figures by Mariusz Galka that identified all the plant macrofossils in the peat slices. I won't go through this too in depth, but just to show how much work has been done already. And of course, there's some charcoal that's been counted to depict the fire history. This is the MAC S3 core, which does show very distinct changes in sphagnum moss. And then there is a period of time here in the middle, I guess at zone, the second zone from the top, that doesn't have much sphagnum at all. And this is MAC S4. And then this is my main focus is testing amoeba. So these are biological indicators that are sensitive to climatic and ecological change. They have been correlated strongly with changes in water table depth. And they're good for this because they're ubiquitous, they're really well preserved, and they respond predictably. They have also been correlated with pH, moisture, and things like arsenic. So this is just a photo of all the different shapes and sizes of the test amoeba that are found. And then I had to count these quantitatively so that I could reconstruct them using a transfer function by Amesbury et al. So this is the water table depth reconstruction for MAC S3, which is the first core that I finished counting. So there has been some debate in the community whether or not we should include idiosomic tests. So idiosomic tests are just those that have been secreted by the test amoeba itself versus agglutinated tests that were created by the test amoeba taking particles from their environment. So it's true that agglutinated tests tend to preserve better, but there's no clear and consistent evidence of differential preservation. And when I plotted both a water table depth reconstruction with idiosomic tests and without idiosomic tests, there are not that many changes. So the reason why this kind of stops at 40 centimeter depth is that there's no more test preserved at greater depth. So even though the MAC S3 core goes down to around 78 centimeters, after 40 centimeter depth, they just disappear, which is probably due to their destruction at depth. What's interesting for this water table depth reconstruction is that there seems to be a drier period starting around the 1600s and up to 1900. So remember that to interpret water table depth is that the higher water table depth means it's drier conditions. And what's interesting about this little peak here is that it coincides with this area where there's not that much sphagnum, and then there's a prevalence of ericaceae roots. So ericaceae is found commonly in acidic and infertile soil, and 1600s to 1900 is considered coincides with the Little Ice Age. So I still have to investigate how the Little Ice Age affected the Western Canadian Arctic. So right now it's just seeing trends without much in-depth investigation. So the next steps, since I'm still counting, unfortunately, because it's super time intensive, is to complete quantification of test amoeba assemblages in all of my peak cores, and then reconstruct the water table depth for all of the cores, and then see if how these trends compare with known ocean and atmosphere interactions, and whether or not we can predict future changes in water table depth as well. And that's just my references. So that's it.